Okay, so basically, so far what we have done is what? And on this assignment, you learn how to find the equivalent springs, no? Because we say that, and the idea of finding equivalent spring is because we find out that for a single degree of freedom systems, we can always reduce the equation of motion to the same type of equation, no? Same form of equation, all right? Then we did the solution of that equation pretty quick. And then last time, upgraded, we had the mass, but in addition to the mass and the spring, we added a damper, no? A viscous damper. We derived the equation, and then it became tedious and a little bit long to find the analytical solution. You remember we had like 3 cases for the damping. If the damping was above 1, it was called overdamp. If it was under 1, it was called underdamp. And if it was equal to 1, basically it was equal to the critical one, no? And we look at some figures to solve what would that do with the motion. All right, so one thing now I need to add, which generally I do it, but if you want, like obtaining, so we were able to obtain the equation of motion using Newton's equation, but let's say obtaining the equation of motion that we call E or M of a damp free system using the energy approach. So guys, please go back to your notes, but let's say recalling the equation that we derive. I think we call it was d dt of partial k. I don't know if I use this partial or if I use the d x dot. Did I put equal or did I put the minus sign? Okay, so I think we use this one plus partial V. This will be the potential energy partial X equal to 0. Is that the equation we had? Okay, so if you move it to the other side, will be the same thing. Okay, all right, so generally, to tell the truth, the way I will do it, I will still use this one, and then I will add the damping at the end. Okay, that's the way I will do it. And adding the damping term it becomes what? So the equation will be d dt partial kinetic energy x dot I'm going to put in the middle plus, and this one has different notation here. Let's say r delta x up dot, and then plus delta v delta x equal to 0. Okay, well, in this equation, I can rewrite this. We know K would be the kinetic energy. V is the potential energy. and R is the dissipation energy. Okay, so to tell the truth, here, to get something new now from that I get from my notes all the time, I just went to online, found one of these examples. So we need to do it. So I don't only have the solution with energy, but we can do it the other way. So let's say example. All right. So let's see. We're gonna have a looks like a pendulum. I guess this could be, this looks like it's been something rigid. All right, there is a damper over here. So this is what we need. Damper C. And here there is a spring. Okay. Okay, so this bar has a mass M. And I mean, this is what they do. Traditional ones, they say this is, put the M over here, okay? They concentrate the mass at this location, like if it was a string. So let's put this one. This will be M at the end. All right, and they have a bunch of measurements over here. So let's say the distance between this point here that we can call O and the spring, that distance, they call it B, the total distance where the mass is, they call it L. Now that distance to the damper is A. And let's say you initially deflect this bar over here by an angle theta. Okay, so the question is derive the equation of motion using, let's say, A, Newton's equations, and B, energy approach, or what is known as the Lagrange, basically. Okay, so let's see, what can we do here? So let's do part A first. So using Newton's law. Okay, so once again, I'm doing this completely live with you, okay? I don't have any solution. So I'm going to show you the procedure. So what type of motion is this bar having? rotation, no? So maybe we can just define the motion of this using what equation? Simplify this, we have this. We have here point O. We're gonna have here, let's say, the damper, which is gonna produce a force now. And we have here the spring. So let's say, what could I do? I could go and A, B, L. Okay. What do we say was the force of the spring? What is the general force of the spring? The X, force of a damper. We say the force of the damper will be proportional to what? C times V, which would be C times X dot, no? Okay, that will be like the force. Okay, so if we say if initially we move it here, theta, this will mean what? That this is going to be the force here of the spring will be push you back in, no? Yep. And then if you put the damper in, force of the damper basically can go in either direction, no? Let's we can go to the left. So let's see, I don't know, here, the damper. Okay, so what could we do over here? We could say this would be step one Fibra diagram. Then we could say the motion would be equal to what? Can take summation of moments about point O and say this is O alpha. I think we already did a couple of problems, no? Okay, so if we take this, what are we gonna have? Okay, you want to start by the forces, so it will be negative F SP. Now be careful because we are moving this a certain amount, no? Yeah. So really our variable here should be theta, no? So let's say if you move it here, what should be the height then? What will be the change in height? Okay, what I'm saying is that if here we are initially here, now when you move it an angle theta, you're going to be here, no? So basically what we're trying to find out is the equation what would be in function of theta. So if theta is equal to 0, correct? Then the value of this moment will be what? Minus F spring times, yes, I didn't put it here, but it should be, no, L, no, it should be B, no? The springs at B. Okay, at 0. But if there is a theta, how does this height going to change? Basically, this is from here to here. Sorry, from here to the spring. What did I put the spring? Okay, whatever would be the spring. Got it. Okay, so if we do it with L, okay, then we can do the other one. That distance over here is not going to be L, no? So what will be that one? Okay, so basically you're on the right direction. You will have what? Cosine theta equal to what? whatever this is moving, whatever this is changing in height, no? Okay, so let's say whatever, L prime divided by L, no? So we were trying to find is the L prime. So this should be equal to what? Minus, okay. So minus FSP L cosine theta. Yeah? Sorry, this should be no LB, no? Yeah, sorry, you see, we're talking so much about L that I forgot. So B cosine theta. Now, the same thing, since I have the speed over here, we need to be careful. I didn't put it here, but we're also gonna have mg, no? When it's moving. So now mg will be creating what? A counterclockwise positive moment or negative moment? We'll be going clockwise, no? So it will be minus what? mg, and this time should be what? L times what? Sine theta. So we took care of that. And what about the damper? Would be kind of similar. What would be the damper? What's the force of the damper? F damper, no? Would be also a clockwise moment. That's what? A what? Sine or cosine? No, sine or cosine? This damper would be moving what? Are we looking about the change in the direction here or about this one here? It would be like the spring, no?
Yeah, so.
Oh wait, did I do here mistakes? Sorry. I think here maybe, I mean, let's just remove, let's just rethink about this. So, yeah, so S spring, L cosine, okay. Now, this one we did mg, L sine, because we're looking at that distance, no? Now, this would be F d spring times A cosine, no? And this should be equal to I sub O alpha. So yeah, everything is too crowded over here. All right, so let me just rewrite this over here. I'll go to the next line. I can rewrite this as what? All right, let me not jump too much at the same time. Let's say it would be I sub naught alpha plus F spring B cos theta minus MGL sine theta, oops, plus, move this into the same side, plus F damper A cos theta. That's it. I'm writing small because I want to make sure it fits. Okay. Now we need to be careful again. So this will be equal to, I mean, let me just do one step in the middle. Here we go. So this will be I sub naught alpha. What is the force of the spring? Is Kx. What will be X? How much would this be moving? Be what? I mean, this is moving on the S direction, no? Okay, so we will have B squared cosine theta sine theta, no? Okay. Then the other one doesn't change, plus MGL sine theta, plus what will be FDP? What will we have? Basically the same thing, no? A cosine theta sine theta. This will be equal to 0. So next, using the small angles assumption, which was what? Correct. Perfect. Sine theta basically is equal to theta, and cosine theta is equal to 1. The above equation can be rewritten as what? And also, okay, I'm not going to do the mistake, so I am not. Can I just put over here that, I mean, we're not this one, that alpha is theta double dot? Is that okay? All right, so we have I theta double dot plus K B square theta plus MG L theta I forgot. Sorry, guys. I did hear. So I was going too fast here. This should not be FDP. This should be already C, no? Okay. And then it should be the last term plus C x squared. And this should be, okay, and this should be this theta dot. Hold on 1 second. Because this is the velocity, so really this is, we had what before? Cosine theta, it should be no sine theta, but sine theta dot. So we have C A squared theta equal to 0. Okay. Okay, so this is part A. This is the equation of motion, E1. Okay. So I say continuous next page. All right. Page 3, so B will be using energy approach which basically is the one we call the Lagrange. All right, so let me redo another small figure here. So we have the bar, it's not perfect, the mass over here. We have the damper over here. C, we have the spring over here. So CK, 0.4. Distance A, distance B, distance F. Okay, so recalling the equation that we just wrote before, which is this one over here. All right. So it's so for x on the equation equal to theta, Lagrange equation becomes what? We have d dt partial k partial theta dot plus partial r partial theta dot plus delta v delta theta will be equal to 0. Okay, so over here, what are we gonna have? We know that K, okay, let's put it again here. The K is the kinetic energy, V is the potential energy, and R is the dissipation energy. Okay, so in this problem, what will be the kinetic energy? What is the general expression for the kinetic energy? 1/2 mv squared, no? Okay, so what will be V? Would be what? So would be theta dot, but we need to be careful because this is like finding the velocity of this one. When something is moving in motion, what is the velocity of something that is moving in rotation? This is equal to what? Okay. So basically it's R times the velocity, no? Okay, so this would be what then? L omega, no? Just like you said. Yeah. Where omega will be, so this will be here, this is rotating at omega, so V at this point here, VA will be omega R, no? And omega is d theta dt, which is theta dot, no? Okay, I'll just give some more details. Maybe I can zoom a little bit on mine. Okay, so we know the kinetic energy. Now we did this before. We need to. This one is probably the most difficult one. What happened with the potential energy? We need to look at the change in this change in height, no? Yeah. So if we look at the mass, this should give us what? If you want, this will be. So let's say it will be mgh. Now, if I do in general, then we find out what h is, no? Plus, I mean, I wrote the general expression 1/2 kx squared, no, for the spring. Correct? So now let's see what h will be. We did this before, but what will this be? Will be mgl. Correct? Yeah? Now, this will be the original one. What will be this one over here? From here to here. MGL what? I mean, we just did it before. That distance from here to here will be what? L cosine theta, no? Yeah, okay. Plus 1/2 k. And now you're going to be correct. What would be the x that this is moving? I mean, we did it before. What should that be? So it will be b what? Sine or cosine? The x movement would be b sine theta. And this should be squared, no? So basically, if you want, what do we have here? So, or V, we can say V will be equal to what? mg L1 minus cosine theta plus 1/2 k d squared and here I'm going to do again the small angular approximation, okay, equal to theta, so it will give you theta squared. Okay, and R over here, this is why I don't like to do this, but Johnny, I just added at the end. The dissipation energy we know is equal to what? Will be equal to 1/2 C velocity squared. So it's kind of similar to the kinetic energy. So it should be equal to what? 1/2 C. What would be the velocity at that point? I mean, same thing we did over here, no? But instead of being L, what would be the distance? A, so we do the same thing, theta dot square okay, so this would be equal to 1/2 C A square theta dot square, and if I do something similar with the kinetic energy at top, will be 1/2 M L square theta dot square. Okay, so now we go substituting. Let me just rewrite the equation. D dt of partial k partial theta dot plus partial r partial theta dot plus partial V partial theta equal to 0. So let's do slowly this. So what will be the first term that we get over here? What will be the partial K partial theta dot? So we do this one over here. L square theta dot, no? Partial theta dot. Okay? Plus the second term will be what? All right, that one's pretty easy. So will be C A square theta dot, no? And the last one, maybe that's the only one we need to be careful. What would be that one? So cosine will be minus sine, no? So we'll get what? Plus MGL sine theta. Oh yeah, plus, I was gonna forget, I almost forgot that one, plus the other term will be KB square theta. Thank you, I almost forgot that one. Oh, interesting, you see? Okay, so this will give us what? L square theta double dot plus C A square theta dot plus K B square theta plus MGL sine theta equal to 0. But again, we can use the small angle approximation and say that sine theta is approximately equal to theta dot. And this will give us what? L square sine theta dot plus KB square theta plus MGL theta plus C A square theta dot. Okay, so if you compare this equation to this equation, what is the only difference? I mean, really they're identical, but basically what happened is that here we already found out the expression for I naught, which is, should be equal to ML square, no? Okay, so otherwise they're identical. So let's say, let's call this equation here 1 and 2. And I will do something else. So go ahead. Because I think I can understand. You see here the DDT. So it's only for that one. Was that your question? Okay. Yeah. So comparing 1 and 2. Let's say the equations are the same, recognizing that I sub O equal to ml squared. Okay, or let's see here. Okay, I'm going to put here as a note. Part B could have been done as follows, and I think will be more correct. Okay, like I'll tell you, this one I just took it from online. This is the solution they give, is correct. Okay, nothing wrong, but personally the way I would have done is this. Okay, so I'm just going to do it very quick because that's probably the way I would have done it, which is basically almost identical. The only thing I'm going to change is one thing: damper spring. Okay, I will have say what? So motion rotation only. Okay, now we'll have say kinetic energy. The kinetic energy due to rotation is what? So motion rotation only about O, no? What is the kinetic energy due to rotation? To translation is 1/2 mv squared. What is it due to rotation? We did this one. It's 1/2 I sub naught omega squared. So this should give you what? 1/2 I sub naught, and we say that omega will be equal to what? L theta dot squared. Which basically now we won't have to recognize this or anything, no? We could just do it that way. Does that make sense? And then, I mean, we'll have for the other one the same thing. Then V will be equal to what? That will be unchanged. We'll have mg L 1 minus cosine theta plus 1/2 K B squared. If I do the simplification, this one now will be X, and the R will be also unchanged, 1/2 C A squared theta dot dot. Okay, and if you substitute, into Lagrange. Okay, let me just rewrite the Lagrange again. D dt partial K partial theta dot plus partial R partial theta dot plus partial V theta equal to 0. In that case, we'll have obtained exactly the same equation that we had before. Instead of having the ml squared, we'll have I sub naught theta dot dot plus K B squared theta plus mgl cos theta plus C A squared theta dot equal to 0. Okay, so the other solution I give you is the one they give on the example. I mean, I'm not lying to you. I'll show it to you if you want, okay? I printed this stuff from online today because I didn't want to do the same examples that I have on the class, I get bored. But personally, you see, I disagree a little bit with that solution, okay? It's correct, but I would say here would be just better to write down, and you see this would be better to write down the kinetic energy, they call it T, this to be equal to 1/2 I sub naught omega squared, no? Does that make sense or not? Yeah, all right. So this should be a 3, 4. So you can imagine what would be your assignment 2. Assignment 2, what I'm going to give you is probably, I don't know, maybe 2, 3, maximum 4. Okay, I think would be 4 would be maybe a bit too much, maybe 3 problems in which you need to find the equation of motion using Newton's equations and the energy method. Okay, that would probably be your assignment 2. Yes. If you can what? Yeah, absolutely. Go ahead. Yeah, I mean, I'm done with this. Yes, and then we can move to something else. I think I put some updates, no, yesterday, because I finished doing the solutions yesterday. Did you look at the? Okay, so maybe let's see. Why cannot I access the page? I think some data was missing for 2 or 3 points. What is that your question? So. Oh, you have to find the Poisson ratio for the other one? Okay, let's look at it. Let's look at it. I mean, generally it's 0.3. I mean, if I'm missing it, oh, because I didn't put it to find the G. I gave the E, but I did not give the V. Okay, good. No, good. So let me know this stuff. So assignments. So assignment 1, because I'm completely making up these problems. So it's I forget data, you know, and I leave it symbolic. So basically for problem 2, you said for this problem. Oh yeah, because I give E and I don't give. Okay, I get it. Yeah. So for problem 3, let me put it over here now. So edit. I need to do those changes. Here, problem 3. For Poisson, should put a capital letter. Do you know what Poisson means? In French, it's fish, Mr. Fish. For Poisson ratio, use. So is the letter mu? Can I just put mu that way equals 0.3? Is that okay? Yeah, I forgot some data, so I was expecting questions. So are your questions also about the data or other stuff? Okay, so let me know. Yesterday I did some of them last week, and yesterday night finished it up. I mean, yesterday afternoon I find out that I forgot some stuff. Okay, so actually a lot of stuff, no, but yes.
Final question. If I use 0.8 for quizzing
yes, please do otherwise. I mean, did you do it by hand or did you put it into a MATLAB code?
I did that one by hand.
Okay, I mean, it's just these problems are pretty simple, no? If you want like a 3 pages problems, I will tell you no. But it's like, okay. All right. So any additional question? Okay, I think basically the idea of the assignment is that you see that you can have a normal. The whole idea was like you start from, you know, like, I mean, more these problems here, that you start from a real structure and you can simplify the model structure into a model of springs, no? Here I didn't put the masses, but you could simplify this into springs or masses. But let's say you have this one into just a set of springs. Yes. 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 But basically you need to be careful because here you have K over L in C. So basically you end up having this system. So you need to find the equivalent of this one first and then do the 3 in series, no? I did unitless because, I mean, I know I put PSI here, but this would be inches. I'll put inches here. That's fine. I mean, I'm more concerned about the process, okay? And really, I wanted you to do it symbolic, everything, but then I said, if I do everything symbolic, they're gonna get mad at me. And that's where I started to forget stuff, because that's when I started to put data. Okay, my idea initially was just to do everything symbolic. I mean, because it's like I told you, like my idea is like not to create a problem that would just have data for one problem, but that you could change, you can make the same problem multiple problems. I don't know, that makes sense?
Yeah.
Okay. So when I was doing MATLAB, when I create my solution, MATLAB is actually to find the general solution. And then upload the data. Okay. Okay. All right. So no more questions about the assignment. So this is due tonight, no? Online. Okay. One thing maybe you have seen, or I don't know if you can see it, but I think I told you this stuff. Yeah. Can you see this? Okay. So basically you see what it is. To me, presentation and neatness is important. Okay. The reason being is because the way you present it on the piece of paper is the way I think is in your head, no? I cannot be in your head, no? So if it's well presented, well organized, I think that's the way it is. If you start putting, like you start one point, you go to the left corner, you go down, you go up again, you send, that's the way I think it's going to be in your head, no? Okay. So it's not only you see everything is procedure. So I won't be the one grading this, will be the grader, but you see, basically, this is what I do all the time. I like procedure. So if I want to see the procedure, I want to see first that is well presented. Okay. And then I want to see the step. Okay. Some type of figure, no? Some type of equations and solving. Okay. In other problems will be this way. Generally, I will specify the steps, no? And this should give you a hint about how to do the solution. That's what. Okay. So make sure you have something for each one of these ones so that the grader can give you points on each one of these ones. Okay. All right. So like I say, assignment 2 would just be, I will pick 3 or 4 problems in which you need to find the equation of motion using Newton's equations and the energy method. You want to do MATLAB? No, I mean, I don't mind doing MATLAB, but let me do first one thing. And then we can move, maybe if we don't do it today, maybe we'll do it next time in MATLAB. We'll do it in class probably. Yeah, probably next time what I'm going to ask you is, remember we found the analytical solution? Okay, I was going to ask you to do in class, I could do it with you, to kind of do a MATLAB code to plot the analytical solution, as well as the numerical solution. So we have what, half an hour class still? Let me try to do something else, and next class tomorrow, that's what we do, okay? All right. I will first show you how to do the numerical solution, and then we do both solutions, we plot them, and we see what is the difference, if any. Okay, so one thing, here is something called the logarithmic decrement. Okay, so basically this is, let me put your notes. On the damp case only. If you remember, the on the damp case, oh, sorry, it should not be that this is the one that gives you the response to be under which form. You start, I mean, I'm going to redo a bigger figure, but this is the underdamped case, no? Yeah, that we derived the other day. Okay, so what happened, and this is what is done in real life is that the question we're trying to solve is how to determine the damping constant C from the response. So basically this means how to determine the damping experimentally. Okay, so Johnny, what will you do to find the damping? If you have a material, you can put it, you can make it cantilever, no? You put it at one location, you deflect a certain distance, okay, and you let it go, no? And you can record with an accelerometer, whatever you want, what will be the deformation, okay? Now, I think it will make sense that if you look at the deformation from the response of the deformation, you should be able to find what is the damping ratio, okay? So that's basically what we're gonna be doing, okay? All right, so let me just redo a figure here. So this is T, this is X of T. Basically, I'm just redoing the figure that we did last time. So remember, right, this should be decrement about the exponential function. Okay, if you want to be accurate, this will be the amplitude exponential minus sigma and T. Okay, and we had here the response. Okay, and so on and so on. Okay. Okay, so here what's important, the other thing we're going to be looking at is that the damping, and generally, I'm just going to do it for one case, but generally will be. So if we look at the amplitude at X1 over here, and compare it to this one to X2, this will give us a damping ratio between 1 and 2, no? Okay? Then, obviously, in this case, we can say it's ideal, no? It's in class, but you can say that then it should be the same damping ratio between X2 and X3, no? Okay? But in real life, the way you will do this is that you will find the C between 1 and 2, 2 and 3, 3 and 4, and so on and so on. And at the end, you will take some type of average. Okay? But in this case, let's just say we do 1. Okay? So let's say over here, so recalling from previous notes. The response X of T is X of T, we write this one equal to the amplitude exponential of minus XC omega and T times sine omega damp T minus phi. Okay, so I'm going to say here, so that in order to find the damping, what I'm going to do is just to find what is the ratio of X1 over X2, no? Okay, so in that case, it will be equal to what? This should be equal to, so this is X at T equal 1, X at T equal 2, whatever that is. All right, so we're gonna have here amplitude exponential of minus xc omega and t 1 sine omega d t1 minus phi divided by the amplitude exponential of minus xc omega and 2 sine omega d2 minus phi. Okay, so if you want me, let's be put over here, figure, this will be T1, this will be T2. Okay, let's see. Now, if you remember, how do we call this over here? So this means that we are on the circle, we go from, let's say, this point here, no? Instead of going back to this point, in this case, we'll go back to another point, let's say that will be here, no? Yeah, that will be the case, okay? But this stuff is called what? This is the period, no? Okay? So that the damn period that we say was equal to 2 pi over omega d. But basically what I'm trying to say is that I could rewrite over here T2 as being equal to what? T2 will be equal to T1 plus the period, no? Whatever time it takes you to get back to the circle. All right? Okay, so knowing this, okay. We can rewrite x1 over x2 as, maybe let me just do here one thing here on the side, to be more specific. So it will be sine of omega dt2 minus phi will be equal to sine omega dt1 plus 2 pi minus phi, which basically will be equal to, let me go here to the line, sine of omega dt1 minus phi. Okay, if you move 2p, you go to the same location. I mean, again, the division is not important anyway, but important here they went down with exponential of minus the damping ratio omega n t1 divided by the exponential of minus the damping ratio omega n t2 so this will give you here exponential of minus xc omega sub n t1 divided by the exponential of minus omega xc omega sub n T1 plus the period to replace T2. And this will be equal to what? So we should be able to cancel this term over here with this one and this one. Yeah. So we end up with exponential of xc omega n, the period of the times the period. Okay, so let's over here. The logarithmic decrement is defined as lowercase delta equal to the, obviously that's what they call it, logarithmic, log of x1, x2, so this should be equal to what? Log of exponential of xe sub n tau sub d. So this should be equal to what? Xe omega sub n tau sub d. Are you done copying the last line? Okay, so I need to go to the next line. 1, 2, 3, 4, 5. Okay, 6. So basically, let me just rewrite this from previous page. What do I have? This is equal to okay, where we said that the period tau sub d was equal to what? 2 pi divided by omega d. So that means that the decrement is equal to xc omega sub n times 2 pi omega sub d. Okay, or here again, if you, okay, you might probably don't remember this one, but the omega sub d was defined as this. So we're gonna get this equal to xc 2 pi omega sub n divided by omega sub n 1 minus x squared. Finally, the logarithmic decrement will be equal to the damping times 2 pi divided by the square root of 1 minus the damping ratio. Okay, so here we have 2 more lines to say, but basically, I'm going to say, I'm going to put here use any mathematical because I'm not going to do it in class. It's not complicated, but I don't think it's the intent of the class. Using any mathematical software, solve above equation for the damping xc, and this will give you the damping xc will tell you is equal to the decrement that you calculated divided by two pi squared plus the decrement you calculated over theta 2. Okay, so let me just finish with one thing. So the damping. So what we're discussing before, that's what I'm going to be saying. Basically, we can calculate the damping just looking at x1, x2, but we could look at x2, x3, x3, x4, and so on, no? Okay. So in general, what you would do is you will not just do one, you will do all of them, and you will take some type of average, no? So the damping ratio XC is generally calculated by measuring the logarithmic decrement for multiple cycles. So basically, you go through one cycle when you go from one peak to the other, no? And taking the average. So basically, I could say, mathematically speaking, I could say that you can do what? The summation from 1 to n, no? Of the logarithmic decrement of x of I divided by x of I plus 1. And all this stuff will be, maybe I can put it here. Divided by n. The number of cases that you do, no? Okay, so that's something else that generally, you can kind of do with MATLAB kind of program. I'm sure that's already been done. Yeah, so I think that's it. So I have a question for you guys, because I mean, I was not in trouble, but some student complained last summer when I was teaching this one, because what is that new class? Did you take that new class ME3 something, which is some type of mathematical modeling? 325, 326. To me, they told me at that time that it was an introduction, that it was mostly Python. Yeah, I know you didn't do Python, but when we discussed this on a meeting, maybe we should not put this stuff online.